Hello everyone, my name is Marcin Ochman and I'm a senior computer vision engineer at deepsense.ai. Today it is my pleasure to be here and give a deep talk about preparing computer vision models for edge devices. Our journey will start with an introduction to edge computing. We will discuss what edge computing and AI edge computing in particular are. What are benefits and challenges regarding on-device computations, and see what's the general pipeline of model preparation for the edge devices. Next, we will briefly talk about computer vision and its main tasks. And finally, we will have an intro to the free frameworks, and we will try to run DeepLab version 3 model on my smartphone using TensorFlow Lite and ExecuTorch frameworks. Let's begin with the presentation, and I hope we will discover the big potential of edge computing. Edge computing is a kind of computing framework, and its main task is to keep data computations as close as it is possible to the location where it is needed. So especially we are talking about on-device data collection and on-device data processing. That means that instead of sending data to the servers, all work is done on device. Similarly, we may define AI edge computing, and it is a type of edge computing, but the processing data module uses AI models internally. There are many devices which are able to run AI models, and these include Raspberry Pi, Nvidia Jetson, Android devices, including smartphones, tablets, even smart TVs, iPhone, iPads, wearable devices, autonomous vehicles, and much more. As you might notice, they differ notably, and because they have various computational power, memory size, or storage capacity. That is why edge computing deployment, especially when we deal with a single model and many devices, may be a very challenging task. So far, we know that edge computing tries to perform on-device computations. Consequently, it doesn't require sending data to the server, waiting for the processing and downloading the results. That means if the model performs well, we have a big reduction in latency. Moreover, it has a big impact on bandwidth savings and therefore money savings, because we don't have to use 4G or 5G network, for example. The big concerns about AI technology is privacy. If the user doesn't want to send, for example, his images or other data to the servers, it seems that edge computing is a great solution to that problem. And finally, edge computing is also power efficient. However, let me explain a little bit more here. First, no connection means power savings, because you don't have to send any data. But on the other hand, running model on device may be power consuming because of the high CPU usage. But if we have an application or in particular runtime, we can optimize it for the given device. So thus we have better power efficiency compared to the server solutions, where often AI applications are not so optimized as it is on edge devices. Despite the remarkable advantages of edge computing, there are also several constraints that we have to keep in mind. First, computing resources are much lower than computing resources offered by the cloud. As a consequence, we have to deal with models which are not so complex. Furthermore, due to limited resources, we have to reduce the size of the model. We will discuss it in the next slides, but it is worth noting here that we have several options for the optimization. for the reducing size of the model, and one of the option is quantization. Next, the integration. It is especially a problem when you have to deal with when you have one model and we have many devices, and there is no framework which can run that model. So it may be an issue if you have many different kind of devices. And at the end, despite the fact that the power efficiency previously was mentioned as an advantage, it is also a big constraint, because when we deal with devices running on batteries, we have to keep in mind that we may run out of power. So the runtime have to take into consideration also the power consumption. So how can we prepare the model? On the slide, you can see the big picture of the pipeline, and in general, this pipeline consists of 4 steps. Let's start with the model choice, because that step is crucial for the whole pipeline, because we have to consider many factors, including complexity, accuracy, and execution performance of the model. So, for instance, now we are not able, for example, to run 70 billion parameters Llama model, so we have to choose something smaller. Then we have to convert our model to the format compatible with the runtime. Optionally, we can optimize our model, and there are many techniques available, and we will discuss it in just the next slide. Finally, the last step is deployment, and basically it is the easiest step, because in most cases it just requires to copy the converted model to some kind of assets directory in your device or in the package, in the application package. As I mentioned before, there are several techniques regarding optimizations of the model, and first, and basically the most popular one, is quantization. In general, quantization is a process which reduces precision of the numbers used to represent the model's parameters. So, for instance, if our model's weights are represented as a 32 bits floating number, we can change that to float 16. So we can reduce the size of the model by half. Moving forward, clustering is another optimization technique. And first, it groups the weights of the model into so-called clusters, and then only one single representative number of the cluster is used to represent the weights of the model. So again, we can reduce the size of the model. Finally, there is an optimization called pruning. And pruning first tries to determine which parts of the model doesn't affect the output of the model notably, and then it tries to remove those parts which are not so important. Generally, when we work with the AI models, we can use numerous AI frameworks which are available. According to the Kaggle State of Machine Learning and Data Science report from 2022, the most popular ML frameworks are scikit-learn, TensorFlow, XGBoost, and PyTorch. Okay, so actually, two of them, namely TensorFlow and PyTorch, has also support for edge computing. So for TensorFlow, it is TensorFlow Lite library, and for PyTorch, PyTorch has 2 of them, and these are PyTorch Mobile, and the new one, and it is called ExecuTorch. Before diving into the frameworks overview, let's talk first about the computer vision and its main tasks. Generally, there are three fundamental, let me call it classic computer vision tasks, and these are image classification, object detection, and semantic segmentation. As you might see on the slide, there are three images representing each problem. In every picture, there is a dog. However, we may notice differences between them, especially in the results. First, it represents the image classification, and the goal of the image classification is to determine what actually is on the image. So that is why we have a dog label below the image. Next, we delve into object detection, and it takes things a little bit farther by not just identifying what's on the image, but it also pinpoints the object's locations within the image. So this is illustrated in the second image, and we have dog label, and we have a rectangular which shows where the dog actually on the picture is. And finally, there is a semantic segmentation, and in general, it is a pixel-based classification. And in other words, every pixel has its own label, and that label represents the object category which that pixel belongs to. Well, actually, we can see that the dog is highlighted in red color. It seems that semantic segmentation is the most complex task among those mentioned problems. So that is why we'll have a demo of the DeepLab version 3 model, which actually performs the segmentation task. Let's move to the overview of the edge frameworks, and maybe we'll begin with TensorFlow Lite. According to the documentation, TensorFlow Lite is a mobile library for deploying models on mobile microcontrollers and other edge devices. On the right, we can see an illustration of the TensorFlow Lite architecture. And the first component is converter block, and it is responsible for converting the TensorFlow model to the compatible TensorFlow Lite model. Then we have an interpreter, and it is responsible for reading the exported converted TensorFlow Lite model, and then it performs operations which are implemented basically in those, let me call them backends. Actually, there are several backends supported by TensorFlow Lite, and these are CPU, mobile GPU, Android NN API library, Android Hexagon DSP, and Core ML. So I think it's quite a big range of devices, wide range of devices. Okay. Let's bring back the general pipeline of the edge model preparation, which consists of 4 steps. And the first step was the model choice. In TensorFlow, there are actually 2 possible ways of getting the model. First, we may use pre-trained TensorFlow Lite model available from TensorFlow Hub. And well, actually, it is already converted model, so it is ready to deploy on your target device. And the second way is rather more complex, and we can create a new model from scratch and then export it to TensorFlow Lite. However, it is worth noting that TensorFlow Lite does not support all operators which are available in TensorFlow. Consequently, there are some models which may not be converted to TensorFlow Lite format. So during the creation process, we have to be very careful. To ensure that the model is compatible with TensorFlow Lite at creation step, there is a tool called authoring in TensorFlow, and actually it is responsible for monitoring and notifying developer if there is a possibility to convert our original model to the TensorFlow Lite format. Next, there is a conversion step, and to convert the TensorFlow model, first we have to get a model. So in this scenario, we have a DeepLab version 3 Plus model, which was built with Keras, and then we have to use one of available methods from TensorFlow Lite converter class. And because we deal with DeepLab version 3 model built in Keras, we use from Keras model method. And then first we have to call convert method to get TensorFlow Lite model, and finally we can save our model to file. And what is worth mentioning that TensorFlow Lite models have TF Lite extension. Additionally, TensorFlow Lite format supports metadata. So, for instance, we can provide additional information for the model, and they may be read by the runner. So, for example, we may save mean and standard deviation values to the metadata. And then the runner may normalize the input tensor. So we don't have to deal with the normalization by ourselves. The first step is optimization, and as we mentioned before, quantization is the most popular technique of the model optimization. And in TensorFlow Lite, quantization is actually part of model conversion. And to perform the quantization, we only have to add a single line of code. In converter, there is a field called optimizations, and we can specify those optimizations. And the optimized default flag means that we will perform dynamic quantization of the model. So as a result, we obtained 4x reduced size of the model. Okay. Before model deployment to the target device, it is worth checking if our model performs as it was intended. And to run our TensorFlow Lite model on our PC, we can use TensorFlow Lite support package. And again, that process is very straightforward. We only have to read our model from the file, and then we can call segment. Segment method to perform the segmentation. And on the left, you can see the result of that segmentation. Finally, we can deploy our model to the target device, and as it was already mentioned, the deployment actually is a process of copying TensorFlow Lite model into some kind of assets folder. TensorFlow Lite supports many languages because it has many bindings, including Python bindings, Java, Kotlin, and C++. So as a consequence, the models may be executed on a wide range of devices. Now let's move to another framework, and that framework is called PyTorch Mobile. Authors claim that PyTorch Mobile is an end-to-end workflow from training to deployment for iOS and Android mobile devices. Actually, it's not 100% true, because PyTorch Mobile also supports Linux devices. The main difference between TensorFlow Lite and PyTorch Mobile is that PyTorch Mobile supports all operators from PyTorch. So as a consequence, PyTorch model can be converted to PyTorch model can be converted to PyTorch Mobile, and we don't have to be care about that. We don't have to be care about the conversion possibility. It also supports a variety of backend, and those are CPU, an N API, Core ML, Metal GPU, and Vulkan. And on the right, there is a workflow of the PyTorch mobile model preparation, and basically it is very similar to the general pipeline we have discussed before. Once again, let's go through the steps of the general pipeline and how can we get the model. There are also two similar ways compared to the TensorFlow Lite, and we can get pre-trained. First, we can get pre-trained model, and it is noteworthy that there are also quantized models, so they are already optimized. And the second way is to create a model from scratch. The conversion of the model is a little bit more complicated because now we have to call actually three functions, but still it remains. I think it still remains simple. First, we have to trace the model. Then we call optimize for mobile function, and finally we can save it to the file with ptel extension. To perform the quantization, there is also dedicated functions for that. And for instance, if you want to perform dynamic quantization, we can call quantize dynamic function. Finally, let's briefly talk about ExecuTorch. And according to the documentation, ExecuTorch is an end-to-end solution for enabling on-device inference and inference capabilities across mobile and edge devices, including wearables, embedded devices, and microcontrollers. One may ask why PyTorch ecosystem offers two various frameworks. The differences between them are quite significant. First, ExecuTorch has smaller memory footprint, and the second, it doesn't rely on torch scripts. So that is why ExecuTorch is expected to perform much better than PyTorch Mobile. However, we have to keep in mind that ExecuTorch is currently available only in preview version. So it is at the moment it is not production ready yet. Because ExecuTorch is still in preview version, the API still is unstable and actually changes a lot. So for that reason, we will not dive into the code of ExecuTorch. Okay, so finally, there is a time for a demo. I have prepared two examples of image segmentation with DeepLab version 3 model. And first, let's have a look at TensorFlow Lite example. Okay, so you can see here is my display. This is my Android device, and as you might see, first, as I already mentioned, there is a directory called assets, and inside that directory we have our converted and optimized model, and it is called DeepLab version 3 TensorFlow with TF Lite extension. The app is very simple. So let me show you two things. The first thing is creation of the model. And reading the model. So first we have to call create from file and options function that creates the image segmenter, and then we can call our segment method to segment that the image. So first, let's start the TensorFlow Lite demo, and as you probably may see, the image is segmented, and well, actually, my monitor shows that the TensorFlow Lite shows that my monitor has labeled it as a TV. So basically, it's true. So that was the first model. What is worth mentioning that that inference time of the TensorFlow Lite is about 30 to 40 milliseconds, and we can also use an API. But we actually in this scenario we don't have we didn't get much boost. So that was the first example, and the second example is ExecuTorch. Okay, let me change the Android Studio window. Here we have ExecuTorch demo, and again, here is the content of assets directory. What is worth mentioning that in ExecuTorch we have two models, because there is a XNNPAC version, and actually it is CPU based implementation. And then we have a model for Qualcomm backend. So basically, in the ExecuTorch we have two models. Okay, and to run our application, we'll start. Just it takes a while. Okay, and as you might see, we have a dog, and there are actually two backends. First, maybe let's start with XNNPAC because it is much slower. But let me show you also the logs. Okay, and let's start XNNPAC. And actually, it takes a while to finish the segmentation, and it took about 4 seconds. I can't see now. Actually, it took about 4 seconds to complete the segmentation. So it is quite a long time. But if we use Qualcomm backends, then it is much faster, and we expect that it will handle that task in just a few milliseconds. So that was quite impressive. So the speed up between the CPU implementation and the Qualcomm implementation is about 500 times. So I think it's really mind blowing. Okay, that's the demo part. Let's move to the presentation. Okay. So what can I recommend you for further reading? First, I think it is crucial to read the documentation of these frameworks. Documentation is a great source of the knowledge, so you will know what's possible, what are different techniques you can apply to your models. Then I can also recommend you some kind of resources related to the target development. So if you're interested in Android deployment, then you can learn, for example, Java, Kotlin, and overall Android environment. On the other hand, if you're interested and you want to deploy models on iOS, then learn Swift and Apple ecosystem. Finally, I have to mention also C++, because C++ is crucial for edge computing, especially in maintaining high performance. So to read or understand or optimize the runtime, I think it is crucial to know that language. Okay, so just to summarize. We have explored edge computing, its benefits and limitations. We have overviewed edge model preparation pipeline. We have discussed AI model preparation with TensorFlow Lite and PyTorch Mobile. We have showcased live demo, and we have run the segmentation model on Android device. And quick notes from mine. The TensorFlow Lite seems to be the most stable and refined framework with a great documentation. PyTorch Mobile is a good choice for PyTorch ecosystem. And finally, ExecuTorch is being developed actively, and it looks very, very promising, but at the moment, it is not production ready. I hope that the past 30 minutes have not only been informative, but also engaging for each of you. I also hope that you enjoyed my presentation, and thank you very much for joining me today. Thank you once again.